Hey guys, so in this video I'm gonna go over a simple proof of what happens when you apply relativity to energy. So we all probably know like the famous equation E equals mc squared, right? But like how many of you actually know where this equation comes from, or how you can derive it? So that's what we're gonna do in this video. So I'm kind of gonna like break the video down into a few parts. So like first of all, you have to understand what is relativity before you can actually apply it to energy. So I think like one of the most common ways you might see relativity be explained, especially time dilation, might be like somewhat like imagine you have a clock that would tick by sending this light pulse straight from here to this mirror, and then it would reflect it back down, right? And so in relativity, we introduced the notion of reference frames. So in this reference frame, the clock that we are calling or imagining here is at rest. So the distance between the two plates is 1 meter. Let's just do that for simplicity. And this light beam or pulse is traveling at speed c, which we know is the speed of light, right? So we know from the basic equation that velocity is distance divided by t naught. Because in relativity we work with different kinds of reference frames, I'm gonna let t naught be the proper time, or in other words, when the clock is stationary. And so coming back to this expression, we can write that the speed of light is then just equal to the distance, which is 1 meter, divided by t naught. And then t naught is equal to 1 over c. But we must multiply that by 2 because it should go tick and then tock, right? That's like the 1 second, or like one, I don't know, light second, whatever you would want to call it, but the time that it would take to return where it was emitted from. So therefore we can define the proper time to be equal to 2 over c, right? Okay, now imagine that there's another stationary observer, right, who witnesses the clock zooming past them, right? And this clock, this time, it's moving at a speed v. So you are still a reference frame because you're stationary, right? But in like the observer's reference frame, these ticks will actually happen at different positions, and that is covered a bit more in Lorentz transforms, but we're not really gonna go in that sector area. But if we had to draw like a rough sketch of what we would see, okay. So I have these three states, right, where this stationary observer might view from, right? So say the light beam would be emitted from here, but as it's moving at speed v, it would have to travel in also the x direction as well as the y direction. So it kind of goes diagonally, right? And then it would reflect off here and it would hit here. So now let's try fill in the gaps. We already know that the distance between the two beams is 1 meter, and this distance here is just going to be the speed of light times the extra time that it took. And then of course, on the x direction, this is just the velocity of the mirror times time. So we have distance here, distance here, distance here. Nice. So now what you might notice is that we actually have a right angle triangle, right? So our triangle looks like this. So 1 meter, velocity times time, and the speed of light times time, right? And so we can apply Pythagoras to this. And so the x component squared plus the y component squared will give us this component, the hypotenuse squared. So if we just write that out, then we're going to get v squared t squared plus 1 is equal to c squared t squared. And now let's try to isolate t, right? So if I take the v squared term to the other side, I'm going to get 1 is equal to t squared bracket c squared minus v squared. And so then t squared will be equal to 1 over c squared minus v squared. And before we take the square root, I think it might prove convenient if we just factor out a c squared in the denominator. So that's going to look like this. 1 over c squared, bracket 1 minus v squared upon c squared, right? They're exactly the same, but it's actually because when we take the square root, then we can sort of eliminate that c squared and turn it into a c, because we're taking the square root. So then if I take the square root, I'm going to get t equals 1 over c times 1 over the square root of 1 minus v squared upon c squared. But I must multiply this by 2 because this right angle triangle is only accounting for half the case. Whereas if we go back to our initial example, we accounted for where it hits the top and then it comes back to the bottom. So then our expression is going to become t equals 2 upon c times 1 on square root 1 minus v squared upon c squared. Now notice that this 2 upon c term here is none other than the proper time that happens when the clock was stationary. Therefore, we can write t equals t naught times 1 over the square root of 1 minus v squared upon c squared. And if we just say let gamma equal 1 over square root 1 minus v squared upon c squared, then we get the expression t equals gamma t naught. And so what it's pretty much trying to say is that the faster you move through space, the slower you will move through time, and that different viewpoints will observe different things at different times. So, okay, we've got relativity kind of nailed, so that's out of the way. That's nice. The next part is energy. What really is energy? Because if we wanted to know what happens to energy in the limit of really high speeds, which is why we have relativity, then we have to first of all start with energy and somehow bring in energy and relativity. So energy is defined as the integral from your starting position to your final position of the force applied over a distance dx, right? Now, we know that force is just mass times acceleration, which is mass times dv by dt. And so that would become mdv by dt. We also know that momentum is mass times velocity. Therefore, the change in momentum is just mass times dv. So now this mdv is equal to dp, and we have that mdv here. So therefore, we can say F is equal to dp by dt. You might recognize this as impulse from high school or first year physics at uni. So now we can make a neat little substitution to say that energy is actually then also equivalently the integral of the change in momentum with respect to time dx. Okay, but how about now we're kind of stuck with momentum, so we have to kind of squeeze relativity into momentum now. So let's start back with momentum, just the same old, right? We know p equals mv, and then if we just expand it out into the derivative form, we know v is equal to dx by dt naught, right? And so we can actually write dx by dt naught as dx by dt times dt by dt naught using chain rule, and they are exactly the same almost, except one is just written out using chain rule, but they will simplify to the same thing. And so if we go ahead and write that, we're going to get p equals m dx by dt naught times sorry, hold on, that should be m dx by dt times dt by dt naught. Earlier, if you remember, we derived an equation t equals gamma t t naught, right? And so if we just differentiate both sides, we get dt is equal to gamma dt naught. And so dt by dt naught is just equal to a factor of gamma. Okay, so p is equal to gamma m, and then dx by dt is just velocity, so we can write gamma mv. Nice. Okay, we've got relativistic momentum. So the next step is where things are going to start getting a little bit more tricky, right? So let's kind of now our new part is, if we had to title it effectively, the search for dp by dt, right? So we want to find what's dp by dt of this. So we know p equals gamma mv, right? Let's expand that out. So that's just going to become mv and then 1 minus v squared upon c squared to the minus a half, right? And so then dp by dt, will be equal to m times the time derivative of v minus a half, right? Okay, so now the kind of trick part here is to recognize that this is actually just a product rule. So recall that if you have a function f and g in terms of x and you will differentiate it, then you're just going to get f dash g plus fg dash. Okay, so in this case, our first function is v and our second function is this. Also, just to be clear about one thing, velocity is a function of time. So that's how we're able to take the time derivative. So if we go ahead and expand and start actually applying product rule to this, so we're going to do the derivative of this times this. And then, okay, I'll come back to that. So the derivative of this will just be m dv by dt bracket 1 minus v squared upon c squared to the minus a half, plus now it's going to be this times the derivative of this. So we can take the m out, so mv, and then d by dt of 1 minus v squared upon c squared to the minus a half. And so if we just continue with the algebra, the calculus actually, then plus mv, and then differentiating this with respect to time. First, we're going to differentiate normally, so we're going to bring out the minus half down, and then 1 minus v squared upon c squared, and then take off one off the power, so that's going to become minus 3 over 2 multiplied by the derivative of the inner function, which is going to be minus 2v on c squared dv by dt, because remember we have to take the derivative of velocity because velocity is a function of time. And so neatly, the minuses will cancel and the 2's will cancel, and so we're gonna get m dv by dt 1 minus v squared upon c squared to the minus a half, plus, so we've got an mv term here, and then we've got a v, so it's going to become mv squared divided by c squared times 1 minus v squared upon c squared to the minus a half, no, minus 3 halves, dv by dt, right? Okay, and the first thing I noticed is we have a m dv by dt in common, so I'm going to factor that out. So dp by dt equals m dv by dt bracket 1 minus v squared upon c squared to the minus a half, plus v squared upon c squared, and then 1 minus v squared upon c squared to the minus 3 halves. Okay, and so the first thing you should recognize is from earlier we mentioned that we defined that gamma is equal to 1 over the square root of 1 minus v squared upon c squared, which is the same as 1 minus v squared upon c squared to the minus a half. So we have that gamma showing up here. So let's start making some substitutions. So dp by dt equals m dv by dt, and then gamma plus v squared on c squared times, now this 1 minus v squared upon c squared to the minus 3 over 2 is just gamma cubed. So we have a factor of gamma cubed. And so we've already got two gammas. I'm just wondering, is there a way I can get v squared upon c squared in terms of gamma? So of gamma. So actually notice how in our equation for gamma, we have gamma equals 1 over square root 1 minus v squared upon c squared, right? So what if I just said let x equal v squared upon c squared? In that case, then we're just going to have 1 minus x. And so if we go ahead and square both sides, gamma squared equals 1 over 1 minus x. And then swap gamma squared and 1 minus x. Then we're just going to get 1 minus x is equal to 1 over gamma squared. And therefore x will just be equal to 1 minus 1 over gamma squared. Okay, and so let's just go ahead and substitute that result back in here. So dp by dt is equal to m dv by dt of gamma plus gamma cubed bracket 1 minus 1 upon gamma squared. And expanding this is just going to give us m dv by dt, and then we're going to get a gamma cubed minus gamma cubed over gamma squared, which is gamma. So we're just going to get a plus gamma and a minus gamma, and those will cancel out. I'll write it out fully though. And so this and this will just cancel. And so we've found successfully dp by dt equals gamma cubed m dv by dt. Nice, nice, nice. Okay, cool. I feel like we're getting somewhere. So for the next part, now we've kind of found dp by dt, we're mostly set because I don't think there's much else we have to find other than probably do some basic integration, because if you recall from earlier, energy is equal to the integral from your starting to your final of dp by dt dx. So I'm just going to actually bring this over to the left side real quick. And then we can write that as going to be the integral from x1 to x2 of gamma cubed m dv by dt dx. Now the first thing I'm going to probably do for convenience is a change of variables. So I'm just going to swap dx with dv, and that will also mean that I have to change my the limits or the boundaries of my integral. So that I'm just going to change it from 0 to v. So it will become gamma cubed m dx by dt dv. Okay, and then we should recognize that dx by dt is just equal to v. So energy is equal to the integral from 0 to v of gamma cubed mv dv. Okay, so the next step is to expand out the gamma cubed. So 0 to v of v, because mass is constant, I'm actually going to pull it out of the integral. So m times v, 1 minus v squared upon c squared to the minus 3 halves dv. Okay, how are we going to integrate this? Is it going to be integration by parts? No. Why? Because actually, if you notice, the first thing I noticed was actually this v that's outside is actually a derivative of the inner function. Remember how if we differentiate the inner function, we get minus 2v to the first power, which is what we also have outside, which means that we can just apply the neat little trick of reverse chain rule, or in other words, guess the antiderivative. So what I'm going to do is, we know that generally the power rule just adds 1 to the power and divides by the new power, right? So all I'm going to do is guess that. So we're going to just add 1 to the power. we're going to add 1 to the power, so we're going to get 1 minus v squared upon c squared to the minus a half. And then what I'm going to do is I'm just going to differentiate that with respect to velocity, because I'm integrating with respect to velocity. So I want to do the reverse to find the answer. And see what sort of factors show up. So if we differentiate that, we're going to get a minus a half, 1 minus v squared upon c squared to the minus 3 halves times negative 2v on c squared, because that's the differentiation of the inner function. And instantly the minus and the minus will cancel, the 2's will cancel, so we're going to get a v upon c squared times 1 minus v squared upon c squared to the minus 3 halves. Okay, so the only thing is we have an unnecessary factor of c squared that's avoiding it from matching with the v. Therefore, we just multiply by c squared. So that means that the integral of v bracket 1 minus v squared upon c squared to the minus 3 halves dv is equal to c squared times 1 minus v squared upon c squared to the minus a half, and plus c if you really want to go that far. But just for the sake, yeah, whatever. And okay, cool, nice. So now we can literally substitute this back with our limits of integration, and we're going to write e is equal to m and then bracket c squared bracket 1 minus v squared upon c squared to the minus a half from 0 to v. And so if we just plug in v, we're going to get mc squared bracket 1 minus v squared upon c squared to the minus a half, and then minus mc squared bracket 1 minus 0 squared upon c squared, which is just 0. So we're going to get that e is equal to mc squared bracket 1 minus v squared upon c squared minus a half minus mc squared. Okay, so the next step is, okay, this is some sort of like energy that doesn't really depend on the velocity. So this can kind of contribute towards the total energy of the system, right? So if we write let E plus mc squared equal the total energy of the system, which will then be equal to mc squared bracket 1 minus v squared upon c squared to the minus a half. Now, remember how this this term here is actually just gamma, right? So therefore, we can just write that E total is equal to gamma mc squared, right? Nice, okay. And the reason why it's commonly called the rest mass energy is because actually if V equals 0, then you're just going to get E rest is equal to mc squared, because 1 minus 0 squared upon c squared times mc squared is just going to give you mc squared. Therefore, that is how you derive the famous mass energy equivalence, probably in a more simple way. I'm actually not sure how Einstein did it, but yeah, yeah, that's how you derive E equals mc squared.